In the dynamic chessboard of modern combat aviation, longevity and reliability are as crucial as speed and thrust. For decades, the GE F-110 engine has been a cornerstone, powering a significant portion of global F-16 and F-15 fleets. But what happens when the technology of a legendary champion faces the relentless march of time? The demands of military operations and the aging of the fleet inevitably led to a critical point. After more than 2 decades of rigorous service, earlier F-110 variants, such as the -100 and -129 models, began to exhibit predictable wear and life cycle issues. Airframe structures like the F-16, however, were slated to operate until at least 2025. This created a critical need: to extend the viable service life of the engines to match the projected longevity of the aircraft. The cost of replacing entire fleets of 4th-generation fighters with 5th-generation aircraft is astronomical. This is where a strategic and economically viable solution comes into play: the Service Life Extension Program, or SLEP, for the F-110. This program, explicitly described as investing pennies on the dollar compared to acquiring entirely new engines, was not a mere technical aspiration, but a profound economic necessity for the USAF and its allies. To understand SLEP, we must look back. The F-110 was not born in a vacuum. It was the result of the Great Engine War of the 1980s, an intense competition driven by the urgent need of the U.S. Air Force to address critical reliability and maintenance issues plaguing the F-100 engines. GE prioritized a balanced approach, placing greater emphasis on inherent reliability, operability, and sustained performance, a fundamental design choice that would be key to its long-term success. The F-110 GE-100, for instance, delivered a formidable uninstalled static thrust of 28,200 lbf, 125.4 kN, in afterburner. This early focus on durability, to eliminate stalls and dramatically improve durability and operating costs, laid a robust foundation. It quickly became a workhorse, accumulating an impressive record of over 11 million flight hours, powering aircraft for the U.S. military and 16 allied nations worldwide. The F-110 SLEP is a comprehensive GE Aerospace initiative designed not only to extend service life, but to enhance performance, bolster reliability, and fundamentally, reduce the total cost of ownership for air forces. Its key objectives are ambitious: service life extension, enabling the F-110 to power combat aircraft for decades beyond their original design, with projections of another 40 to 50 years of runway. Cost reduction, achieving up to a 25% improvement in cost per flight hour, CPFH, translating to billions of dollars in savings. Reliability and safety improvement, introducing newly designed parts with superior durability. Performance and maintainability enhancement, increasing thrust capabilities and allowing a greater percentage of maintenance to be performed directly on wing. The how SLEP was achieved is a testament to GE's engineering prowess. A full engine refresh approach was adopted, and a strategic infusion of proven technologies, many derived from GE's successful commercial engine programs, such as the CFM56 and LEAP families. In fact, a staggering 92% of the F-110's parts have undergone some form of design change since its introduction. Join us as we delve into the detailed engineering that makes SLEP possible. High-pressure turbines, HPT. The HPT operates under extreme temperatures and immense centrifugal forces. SLEP-infused single-crystal alloy technology offering a significant durability gain and keeping crack propagation in check, especially between 925 degrees Celsius and 1050 degrees Celsius. Advanced thermal barrier coatings, TBCs, and sophisticated cooling technologies, adapted from commercial engines like CFM International's LEAP, are also applied. Combustion chamber. This crucial section has achieved a 2x increase in life. Advanced materials and improvements in cooling and fuel distribution have been incorporated to mitigate hotspots and enhance efficiency. Advanced aerodynamic technology, 3D Aero, one of the most impactful transfers. This technology, derived from the highly successful CFM 56-7 commercial engine, optimizes airflow paths in compressor and turbine components, resulting in greater efficiency and prolonged rotor and structural life. FADEC Digital Control System. The F-110 GE-129B, for example, received a modernized engine digital control, MDC, becoming the brain of the engine. This system processes input variables up to 70 times per second, achieving optimal fuel efficiency, automatic engine protection, and advanced diagnostics, simplifying maintenance. Other relevant components. SLEP encompassed almost every part of the engine. The compressor features a new fan blisk configuration for advanced variants, like the -132, improving efficiency and airflow. Afterburner systems now have a 10-piece segmented flame holder, dramatically reducing replacement time from over 3 hours to less than 20 minutes per segment, improving aircraft availability. SLEP's benefits are not theoretical, they are quantifiable and transformative. Reduced cost per flight hour, CPFH. An improvement of up to 25% in CPFH. This is estimated to yield potential savings of approximately $1 billion for a fleet of 800 USAF F-110 engines and pennies on the dollar return on investment. Increased time on wing, tow. The F-110 has achieved an industry-leading standard of 750 hours of tow. SLEP has achieved a 3-fold increase in average time on wing. Most impressively, 90% of all maintenance can be performed on wing rather than requiring a full engine removal.
When you change technologies in engines and they last longer, then you don't need as many airplanes because there are not as many out of service for maintenance.
Reliability and thrust improvements. SLEP has fundamentally enhanced engine reliability. Furthermore, the F-110 GE132 variant, the pinnacle of the F-110's evolution, offers an impressive thrust of 32,500 lbf, 144.6 kN in afterburner, representing a substantial increase over earlier models. Notably, the -132 can be derated to operate at -129 thrust levels, extending inspection intervals from 4,300 to 6,000 cycles. SLEP has not only extended life, but has catalyzed the development of advanced variants. The F-110 GE129, for instance, powers approximately 70% of the latest F-16C/D aircraft for the U.S. Air Force and allied nations. Its enhanced subvariants such as the 129C, 129D, and 129E offer extended inspection intervals of 6,000 cycles. The 129E has even been selected to power the prototype of Turkey's indigenous fifth-generation fighter, the Taycan. The F-110 GE132 is the latest and most powerful iteration, boasting 32,500 lbf of thrust, incorporating a new blisk fan and a radial afterburner derived from the F-414 engine. GE's ability to offer upgrade kits to convert existing F-110 engines to the -132 configuration underscores the modularity and adaptability of this design. The GE Aerospace F-110 Service Life Extension Program stands as an outstanding testament to modern engineering and strategic planning. What began as an engine born out of necessity in the Great Engine War of the 1980s has been transformed for the 21st century. The $1 billion in savings, the up to 3-fold increase in time on wing, and the capability to operate for another 40 to 50 years demonstrate unparalleled strategic value. The F-110, far from being a relic of the past, is a model for how smart investment in the modernization of proven assets ensures operational capability and national security for decades to come. In the world of combat aviation, where time on wing wins wars, the F-110 engine and its SLEP program continue to redefine air power. Interested in the engineering that powers the future? Subscribe to our channel for more in-depth analyses on aerospace technology.